Hello, welcome to Zeta Explained. Today we are covering Riemann's Xi function and the origin of the Riemann hypothesis. So today we're going to continue to walk through Riemann's original 1859 paper, which is on the number of prime numbers less than a given magnitude. And this paper originally launched the investigation into the zeta function, and this paper is actually where the Riemann hypothesis comes from, and we'll get to that today. And on the left here, we have the Wilkins translation, and I'm going to scroll down to where we left off last time, so this is where the paper begins. And then last time we covered this thing called the functional equation, in the last two episodes actually. And in episode 41, we in fact covered this proof of the functional equation. So this is the second proof. And now we're kind of into the real meat of this paper. So today we're going to cover the next three paragraphs of this paper, where he discusses the Xi function. Xi is defined as follows. Although if you have a very keen eye here, you might notice that this is actually not the definition that Riemann said. So Riemann defines Xi here like this. I'm going to scroll down a little bit more. And so I'll explain why this definition is a little bit different from Riemann's definition. And I'll note that the structure of today's video is, of these three paragraphs that we're covering, the first one is not very exciting. So most of our time is going to be spent on the second and third of these paragraphs. And these are the kind of two of the most interesting paragraphs in the entire paper. And I'll also note that we did cover this Xi function back in episode 17, although our definition there was off by a factor of 1/2 due to our following a different textbook at the time. But today we're following the paper directly, so we have an extra factor of 1/2 right here, s over 2. So if you're confused and you've seen this function before in episode 17, we did not have that divided by 2, but this is kind of the more natural way to do it with this divide by 2 here. All right, so let's get on to the episode. So recall from episode 41, this is just the last episode, we proved that gamma of s over 2, so this is just the left side of the functional equation, gamma of s over 2 times pi of to the negative s over 2 power times zeta of s is equal to this integral minus some terms after it, and then this psi thing is this Jacobi theta function, although you can see that this is not the theta function, theta symbol, but it's still a theta function. And because this thing vanishes exponentially as x goes to infinity, this integral represents an analytic function. And in particular, this thing is uniformly convergent in any kind of bounded area. So therefore, there are two poles of the function. So this part right here, this integral, is like a completely standard and normal thing that doesn't explode to infinity anywhere. But you can see that this thing right here, the 1 over s times 1 minus s, does explode to infinity, and that happens at s equals 0 and s equals 1. So if you plug in s equals 0, you get divide by 0, and plug in s equals 1, you get divide by 0. So we will then make this an entire function. So the point of this Xi function, so I'm trying to motivate what the point of this function is. Instead of dealing with this function, what we're going to do is that Riemann removes these two poles at s equals 0 and 1 by just multiplying by s and s minus 1. And then he's going to additionally multiply by a factor of 1/2, which I'll explain in a sec, to get Xi of s is equal to this. And notice that this part of the equation is exactly the same as the part in the functional equation. So I'm kind of skipping ahead a little bit, so I haven't explained this part yet, but I'm kind of explaining this sentence here. So when Riemann next says this function is finite for all values of t. So in this case, we actually don't have a t, we have an s, but the claim here is that this function right here is an entire function. So it does not equal infinity anywhere because we kind of removed all the poles. Okay, and then I will note that the reason why there's a 1/2 right here is that Gauss and Riemann back in the day used the pi notation to denote the standard extension of the factorial function. So pi of n is equal to n factorial if n is an integer, but obviously you can take this to be a complex number or non-integer as well. However, modern mathematicians usually use the gamma function, which is offset by 1. So gamma of n is equal to n minus 1 factorial, and therefore pi of s minus 1 is equal to gamma of s. So in Riemann's work, you actually see him using the pi function. Now, since because of this function, this equation right here, pi of s minus 1 equals gamma of s, you get the fact that pi of s over 2 is equal to s over 2 times pi of s over 2 minus 1. And this is just our definition of factorial, because if n is an integer, then n factorial is equal to n times n minus 1 factorial. So it's the same thing for the pi function. Pi of something is equal to that thing times pi of that thing minus 1. And because of this equation right here, pi of s over 2 minus 1 is just the same thing as gamma of s over 2. Okay, so therefore we have this equation. And Riemann actually writes this as c of s is equal to s minus 1. So there's no s in front. So you see how here there's an s. He has s minus 1 times pi of s over 2 times pi. This is the 3.14159 constant, whereas this is the factorial function, so it's a little bit confusing. These are both pi's, capital pi and lowercase pi. This is pi to the minus s over 2 times zeta of s. So this explains why there's a factor of 1/2, because if you just kind of expand out pi of s over 2 right here as s over 2 times gamma of s over 2, then you get this equation. So that's why there's a divide by 2. And then if you look carefully, there's still a difference here. So this is still not the same as what Riemann wrote. Riemann actually wrote this thing as c of t, not c of s. So what is this t? So Riemann says I now set t equals, or s equals 1/2 plus ti. So I'm going to call it 1/2 plus it. And then he writes c of t is equal to the thing we had from before. And what this does is explained in this diagram. So what he did is he shifted and rotated the definition, although it's mostly a rotation, in the complex plane by 90 degrees. So if you've been following this video series, you know of something called the critical line. It's kind of the most important part of this Riemann zeta function. And the same thing is true for the xi function as well, since xi is some number of things times the zeta function. And what will happen is that this critical line is where the real part of s is equal to 1/2, so it's a vertical line when we usually talk about it. However, because Riemann did s equals 1/2 plus it, it now actually becomes a horizontal line, and it doesn't have an offset of 1/2. This time, this is just the real axis. So in the t-plane, the critical line from zeta now gets kind of rotated into a vertical or into a horizontal line. So vertical line turns into a horizontal line. And namely, this becomes the real axis. Okay, so in a lot of this text right here that we're going to follow, Riemann kind of refers to like real numbers of t, but he's really talking about the critical line that kind of modern mathematicians would call it. And yeah, in particular, so modern mathematicians regard this as unnecessarily confusing. So like no one does this substitution anymore. And Riemann's original definition is renamed to the uppercase xi. So instead of xi of t being this thing, we write xi of s is equal to this thing. And then this capital xi of t, or uppercase xi, looks like this symbol. I usually don't see it written much, but this is kind of the first instance I've seen it written for this function. Capital xi of t is equal to lowercase xi of 1/2 plus it. So this is Riemann's original definition right here, but no one really uses this anymore. However, I will kind of follow along both definitions for today's episode so we can kind of follow along exactly what Riemann's doing. All right, so let's continue. So in the first of the 3 paragraphs covered today, Riemann actually develops a series representation for the xi function in terms of this Jacobi theta function from last episode. But I'm going to kind of skip this, and the reason is that this part doesn't seem particularly relevant to the next few paragraphs or to the rest of the paper. And it's not a particularly interesting equation. And I'll note that the text we're following from Edwards says that Riemann does not say what role this series plays in the assertions which he makes next. So that's why we're going to kind of ignore this. I'm going to skip this paragraph and then go on to the kind of the real meat of this paper, which is like this paragraph here and then the next paragraph. So this we're now covering paragraph number 2. Okay, so actually, sorry, it's still on this page. So he then says this function is finite for all finite values of t, and we kind of already discussed this before. And the reason is if you take this kind of part for the functional equation from before and this thing that we got from the last episode, you just multiply. Remember the xi of s definition. Let me just go back a little bit. Xi of s is equal to this part from the functional equation times s over 2 times s minus 1. So we're just multiplying by s over 2 and s minus 1. And therefore, when you multiply this whole thing by s over 2 and s minus 1, so we're taking this thing, then the s and s minus 1 will actually exactly cancel out this part, which is inducing the pole. So s over 2 times s minus 1 times this term right here just becomes a constant 1/2. And then the s times s minus 1 doesn't do much to this term. This is already an analytic function, so multiplying by s times s minus 1 is still an analytic function. So now c is now an entire function, because this part vanishes exponentially as x goes to infinity, and we kind of covered that in the previous episode, but I don't want to kind of waste time proving that because we're kind of limited on time right now. So the integral converges uniformly for any bounded region of S, and therefore it is an entire function. Okay, and then I will mostly skip the second part of the sentence, so we're almost going sentence by sentence here. It says it allows itself to be developed in powers of TT as a very rapidly converging series. And Riemann does something kind of interesting where he refers to the square sometimes as he just writes a variable twice. So in particular, he really means t squared right here, but he just writes tt. And then similarly, later on in the video, we'll see he writes tt over alpha alpha, which just means t squared over alpha squared. Okay, but I'm going to kind of skip this part of the sentence. Okay, so next. So we're going to consider the proof that c of s is equal to c of 1 minus s. So before we get to the next sentence, we kind of review this thing, because it's going to be used throughout this paragraph. Remember the functional equation that we proved in the last episode says that if you take this left side here and replace every s with 1 minus s, then you get the right side of the equation. So in other words, this expression remains unchanged if you replace every s with 1 minus s. And now c of s can be written like this. So all I did is I introduced a negative sign in front and I changed the s minus 1 to 1 minus s. And therefore, by this equation, if you just combine these two equations together, you get that negative s over 2 times 1 minus s. Because this functional equation is true, then I can just multiply both sides of this equation by negative s over 2 times 1 minus s. And note that if you change s to 1 minus s, then this part becomes 1 minus s, and this term becomes the s right here. But then this thing on the right is just the definition of c of 1 minus s. So therefore, c of s is equal to c of 1 minus s. And I'll note that this is kind of similar to this statement that Riemann wrote. Riemann kind of either assumes you already know this because you're good at math and when you're reading this paper and you already figured this out from what he wrote before, or implicitly from when he said that this capital C function can be developed in powers of TT. And in particular, if you can write the C function, this uppercase C function, as a power series only in powers of t squared, so there's no odd terms, there's only even terms, that kind of implies that this is an even function. So therefore, capital C of t is equal to capital C of minus t. But this and this are essentially the same thing. Because if you remember, there's a substitution of 1/2 here, so that's why in the lowercase c, there's a 1 minus here, whereas in the uppercase c, it's just t and minus t are symmetrical, whereas here it's s and 1 minus s are symmetrical. Okay, so let's go on to the next part. So sorry about this, is kind of very technical here, but I'm trying to cover like everything that Riemann is saying. So next, Riemann essentially says that there are no zeros of c of s in the regions real part of s greater than 1 or real part of s less than 0. So that's in like this sentence right here. And in other words, any zero must have a real part between 0 and 1. And remember, I'm looking at the s plane, whereas he's looking at the t plane here. Although he refers back to the s plane a little bit right here, so I'll mention what this means, so how he proved this. And he proves using the same method that we used in episode 5 to show that zeta of s has no zeros with real part of s greater than 1. And the proof is basically you consider the Euler product formula for the zeta function, and then you take the log. So this is the Euler product formula. We covered this in episode 4. And the product here is over prime numbers, so p here. And the idea is if you take the log of both sides, then log of zeta of s is equal to log of this thing, but the log of a product is equal to the sum of the logs. And when the real part of s is greater than 1, then this thing is absolutely convergent, so that's what allows you to interchange the sum and infinite sum and infinite product here. So this becomes the infinite sum over the log of this thing, and then using the basic kind of properties of logarithm, log of 1 over something is equal to negative of the log of that thing. And then this is the equation that Riemann wrote right here. So log of zeta of s is equal to negative sum of log of 1 minus p to the minus s. And then the proof, we've already covered this in episode 5, so I'm not going to go over it again, but if you just develop the Taylor series for log of 1 minus z, so this term here, log of 1 minus something, then the result follows for zeta. And also the other terms of xi cannot vanish in this region. So we proved that zeta has no zeros to the right, like in this region, real part of s greater than 1. But remember, there's this pi to the exponential term here, and there's a gamma term here, or the factorial term. But both of those also have no zeros in this region, so we're fine. And using the fact that xi of s is equal to xi of 1 minus s, then the fact that xi is non-zero for a real part of s greater than 1 also implies it is non-zero for a real part of s less than 0. So it's saying that because there's no zeros to the right of 1, there's also no zeros to the left of 0. And if you've thought about the zeta function a lot before, you actually probably know that there are some trivial zeros of the function at negative even integers. And this part right here seems to contradict the thing that you know. And I'm going to claim it's not a contradiction. So note that this statement right here is not saying that the zeta function has no zeros with real part of s less than 0. It is just saying that the xi function has no zeros with real part less than 0. So in fact, the zeta function actually does have an infinite number of trivial zeros, but the reason why xi does not have these zeros is because they're canceled out by the poles of gamma. So I'm not going to explain this too much. We talked about this exact statement in episode 15, but that's kind of what's going on here. So we're just saying that xi cannot be 0 to the right of 1 or to the left of 0, and I'm going to show this graphically. So remember, we have this function, this equation here, xi of s is equal to xi of 1 minus s, and we proved that this proof is relatively easy in episode 5, that there are no zeros to the right of 1, so this green shaded region here. But this equation lets you kind of transfer knowledge of the function from one area to another area. So if you do 1 minus some part of this green region, then you turn that into a statement about this other green region here that's kind of mirror imaged across this line, real part of s equals 1/2. So this is mirror imaged across the critical line here, the dashed line. And note that all of the remaining zeros of either function, the xi function or the zeta function, must be in this remaining vertical strip here, the critical strip. Okay, and then remember, Riemann writes something differently. So he says the function xi of t can only vanish if the imaginary part of t lies between 1/2 I and negative 1/2 I. So why is this the case? Well, it's because, remember, Riemann's version is a 90-degree rotation of this thing. So it looks like this. So capital Xi of t is equal to capital Xi of negative t, where this is the definition. So he kind of just flips it 90 degrees, and therefore he's saying that there are no zeros below kind of negative 1/2 I or above 1/2 I. So this is the imaginary part of t right here. So he converts the vertical strip into a horizontal strip. Okay, let's continue. So the next part is he's going to start counting the number of zeros. So he says the number of roots of xi, and I'll explain what we do here. So again, before we count the zeros, remember the core connection between the zeta function and the xi function. Because the gamma function cancels out the trivial zeros, the roots of xi of s are exactly the same as the non-trivial roots of zeta of s. So if you've heard the Riemann hypothesis before, it concerns these non-trivial roots of zeta, but because these are the same, the non-trivial roots of zeta are exactly the same as the roots of xi. So in fact, the Riemann hypothesis is actually about the xi function, as you'll see in a sec. So the next sentence here, so actually this is quite a long sentence. It goes all the way to right here. So it's right here. Riemann states what is now known as the Riemann von Mangoldt formula. And he says, let n of t be the number of zeros of imaginary height between 0 and capital T. So that's this purple region here. So we're looking at the critical strip. We're going from 0 up to some value T. And then this formula tells you how many zeros there are in this region. So in the drawing, there's like 2 zeros right here. But as you take T to higher and higher and higher numbers, then there are more and more and more zeros. And they actually get closer, like kind of more bunched up together as you go higher. So we have n of t is equal to t over 2 pi log of t over 2 pi minus t over 2 pi plus big O of log of t. So there's just an error term that grows like log of t. And then, of course, if you look at Riemann's formulation, it's a bit different. Remember, Riemann actually is going to flip it to be a horizontal strip instead of vertical strip. But one thing I do want to mention is if you kind of read here how Riemann tries to prove it, he says that the reason this is true is because this integral of something d log of c of t taken in a positive sense around the region consisting of the values, and then it gets very, very complicated here. I'm not even going to read this. Is equal to something, and then this integral, however, is equal to the number of roots. And this proof is actually extremely complicated. And in fact, it was not proved until 1905 by von Mangoldt, and that's 46 years after this paper. So either he kind of got the correct proof here and left out all the details. Maybe he assumed that the method here is so easy that anyone can do it, but evidently he was wrong because no mathematician could actually prove this for 46 years. So this is kind of a deep result, but I think Riemann was also known as kind of a master of doing integration, especially like contour integrals. So if you want to see an actual proof of this, we covered this in episode 21. So episode 21 was just proving this one equation, but it was like an hour and 10 minutes long. So that shows how deep of a result this is. But Riemann kind of just casually states it in one sentence and giving you some instructions of how to prove it, but then it's actually quite hard to actually prove it. All right, so as I mentioned, so we're going to translate this into the t-plane instead of the s-plane. So we're rotating it by 90 degrees. And now, actually, let me go back for one sec. So remember, if you probably usually know of the Riemann hypothesis as the statement that all of these non-trivial zeros in red are on the vertical line, real part of s equals 1/2. But when we flip it using kind of Riemann's version of the C function, it now changes into a horizontal line. So the Riemann hypothesis becomes a statement about whether all these zeros are on a real line, as we'll see immediately, in a few minutes, or maybe in less than that. And now, when Riemann says the Riemann von Mangoldt equation, the strip here gets converted to a horizontal strip. So the zeros up to height t now lie along a horizontal strip between real part of t equals 0 and real part of t equals big T. And that's what he's saying here. So whose real parts lie between 0 and t is approximately this same formula. Cool. Okay, and then finally, we get to the Riemann hypothesis. So this is the most critical line of the entire paper from, I guess, modern standards. So he says this. So I just kind of rewrote the sentence right here. He says, one now finds indeed approximately this many real roots within these limits, and it is very probable that all roots are real. And I split this sentence into two parts because this is actually not just saying the Riemann hypothesis. There's kind of a weaker statement first and then the Riemann hypothesis. The Riemann hypothesis is the second statement. And here are the two statements. The first statement, it's not super clear what he means by this, what he means by the word approximately or about, depending on which translation you use, because remember this was originally written in German. But a lot of people believe that what he meant here is something equivalent to something that might be known as the 100% hypothesis. So he's saying that he found a formula for the number of zeros in the whole strip. So up to kind of like in this whole strip, if you go to the right and t gets very large, then n of t is this number. And a kind of way to interpret this statement is that Riemann kind of somehow figured out that the number of zeros along this line is also this number right here, is also the same formula. And therefore, he says one now finds indeed approximately this number of real roots within these limits. And therefore, you could formulate that as saying that 100% of the zeros are on the critical line. And then the Riemann hypothesis is the second statement. although he doesn't actually claim he has a proof of this. So in everything else, he kind of talks as if he's proved everything. But right here, he says it is very probable that all these roots are real. And then he has some things that later say, like, certainly one would wish for a stricter proof here, but I put it aside after some fleeting futile attempts. So he does admit that he doesn't know if this is true, and he hasn't proved it. And the Riemann hypothesis, of course, is that all zeros are on the critical line. And in this version of it, it means all of these zeros are on the real line, the horizontal real line. It's this blue statement right here. Okay, so if you've been following so far, you might be wondering what's the difference between these two sentences. Like the red sentence says 100% of the zeros are on the critical line, and the blue sentence says all the zeros on the critical line, but don't these mean the same thing? Like why would Riemann kind of phrase these as two different things? Okay, so the answer is that 100% in math doesn't mean the same thing as all. So you have to be very careful in things like this, in probability theory or number theory or things, I'm sure many other fields of math as well. The 100% really means the phrase almost all, although that probably doesn't help you either. But it's the same sense in which 100% of all real numbers are irrational. So if you pick a number at random, on the real line, you can have an irrational number or a rational number. But from some basic set theory, there are way more irrational numbers than there are rational numbers. So if you kind of just pick a real number at random, the chance of getting a irrational number is 100%, even though obviously there are an infinite number of rational numbers as well. And then similarly, you could say that 100% of positive integers are not square numbers, which are like the numbers 1, 4, 9, and 16, and so forth. And this is just saying that the density of these numbers kind of goes to 0 as you go higher. So obviously, if you went to only a finite range, this is not true because you can always find some numbers that are square numbers if you go from 1 to some finite range. But if I'm saying for an infinite range, then like almost all positive integers are not square numbers. Okay, but enough about this word almost or 100%. This thing is still an open question. No one knows if this is true or not. And here is the progress so far. So in 1914, Hardy proved that there are indeed infinitely many zeros along the critical line. So remember what Riemann had before is that he actually found the first 3 zeros that are on the line. But what's to say that even if this equation is true, then at some point there stops being zeros on the line, and then all the zeros are kind of, somewhere else in this strip but it's not on the line. So it took until 1914 to prove that there are actually an infinite number of zeros on the critical line. And then Selberg proved in 1942 that at least some positive percent of the zeros are on the critical line. And then the progress has been kind of slow since then. So our best bound right now is at least 41.73% of the zeros are on the critical line. So there's still a lot of progress to be made before we get to the 100%, although it seems like possibly Riemann thought that this was just true. And perhaps he had a proof for it, but likely not, given how difficult this is. And now it's more than 150 years later. Okay, and then of course we have the Riemann hypothesis. And the Riemann hypothesis is much stronger than the 100% hypothesis. Riemann hypothesis says that literally all zeros are on the line. So both of these statements, the examples we used before, are false if you kind of go to Riemann hypothesis level. So it's not true that all real numbers are irrational, just 100% of them are irrational. And then similarly, it's not true that all positive integers are not square numbers, just that 100% of them are square numbers. And this is a table of verification results. So Riemann proved that the first 3 zeros are on the critical line back in 1859. And to kind of figure this out, like we mentioned, we spent episode 29 figuring out how to visualize or compute or verify the Riemann hypothesis. And we discussed using the Riemann-Siegel z function and gram points to compute zeros of the zeta function. And note that many of these results are even before the age of computers. So right now it is known that the first 0.2 times 10 to the 13 zeros are all on the critical line, so they all satisfy the Riemann hypothesis. So no one knows if this is true or not. And you can win $1 million if you can prove that this is true or false. But it is true up to the first 10 to the 13th zeros. All right, so we're kind of continue here, and I think I have one note at the very bottom here. And Riemann then says that these two claims are not needed for his goal of studying prime numbers, so he kind of moves on. So he says, it appears unnecessary for the next objective of my investigation. So remember, he's eventually gonna get to prime numbers, but there's still one paragraph left before he gets to the prime numbers. So that's the last paragraph we're gonna cover today, the third paragraph. Okay, so this paragraph might be the most confusing paragraph if you haven't really read like number theory papers before. So even the paragraph that we just did, it's very difficult to read, but at least like some of the things make sense. Like this statement, it is very probable that all the roots are real. If you think about it hard enough, you can probably even on your own, like without talking to any professors or anyone, like kind of see that this is saying the Riemann hypothesis. However, the next paragraph is kind of difficult to read unless you actually know what he's talking about, like the subject matter. If you just start trying to read the sentence, it's like the density of the roots grows only as this, and then what is this like sum of logs doing? So I'll try to explain what's going on here. So Riemann is trying to write a product formula for Xi in terms of its roots. And to figure out what the point of this even is, let's actually return all the way back to episode 1. So in episode 1, we covered Euler's infinite product formula for sine of x. Sine of x has zeros at 2 pi n for every integer n. And sorry, I think I made the same mistake here as in that episode. This should just be pi n, not 2 pi n. So sorry about that. Because obviously sine of x is 0 at an odd multiple of pi as well as an even multiple of pi. Okay, so sine of x has zeros at pi n for every integer n, and therefore he factorized the function sine of x over x as this infinite product. And the way that this works is that each denominator is a 0 pi n squared. And the reason this is because there are zeros for every positive and negative integer n. So if n is like 1, then there's sine of x is 0 at both positive 1 pi and negative 1 pi. Okay, so this is the factorization of the sine function. And many times we prefer to work with sums rather than products. So we're going to take the log of both sides. So log of this thing is equal to log of this thing. And then I'm just going to claim that we can write this. The log of a product, infinite product, is the infinite sum of the logs without any justification. And indeed, the justification is kind of the problem that Euler's kind of method had. So using modern standards, we actually wouldn't consider this to be kind of a rigorous thing that Euler did, but we're just going to kind of continue on for now as if we can do it. Another way to state this formula right here is that if the Greek letter rho denotes the positive zeros of this function, so f of x equals sine of x over x, then log of f of x is equal to the sum over rho of log of 1 minus x squared over rho squared. Because remember, it has zeros every pi n. So pi n squared is just like pi squared, then 4n squared, then 9 pi squared, and so forth. So I'm saying this thing is just can be written like this if you want to make it more abstract. Okay, and then now you can kind of see what Riemann wrote here. So this thing right here, I'm just going to put it on the screen as well, looks exactly the same form as this thing. So log of f of x is equal to this thing for the sine function. And then Riemann, like Euler, assumes that you can factor a function with an infinite number of roots into a product. And therefore he writes, using alpha to denote the positive roots, as log of Xi of t. Now I'm now switching back to Riemann's form to try to explain where this equation came from. So capital Xi of t is equal to log of capital Xi of 0 plus the infinite sum over alpha of log of 1 minus t squared over alpha squared. And hopefully this equation kind of makes sense. So if you feel like you kind of understood this, the sine formula from episode 1, then this kind of looks the same thing as this formula. And then the log of Xi of 0 here, the point of this term is that the product might not be the correct product. So for example, if I wanted the function 2 sine of x over x, then this is the wrong formula because I need a 2 in front of this infinite sum, right? And then if I take the log of both sides, I need a like log of 2 in front of all this. So this is just saying that there might be some like constant offset here because we might be, the original like factorization might be off scaled by some constant factor. Okay, so this is what Riemann assumed you could do. And then the whole paragraph here is spent trying to justify why this is a valid equation. I.e., so there's two things you have to do. So one is why the sum converges, and then two, you have to show that this is actually correct, as like there's not some other factor going on. Like for example, you could say sine of x over x times e to the x, and that would still have the same zeros as this, but then this would no longer be a correct product. And even if you added a constant in front, it still would not be a correct product. Okay, so there's two problems here. And then decades later, the Weierstrass factorization theorem and the Hadamard factorization theorem would actually justify this. But this is Riemann was trying to do this decades before this existed. And we, in fact, covered these two theorems in episode 20 and how this Hadamard factorization of the zeta function occurred. So you really, really find this thing interesting, check out episode 20. But I'm going to move on for now. Now I'm going to say both sine of x over x and the capital C of t are even functions. So remember, c of t is equal to c of negative t. Now sine of x is usually an odd function, but if you do sine of x divided by x, that's an even function. And so therefore, for both of these functions, a 0 corresponds to a negative 0. So therefore, I'm going to write the sum as follows. So I'm going to allow alpha to range over all zeros, as opposed to only the positive zeros. Then really what's going on is that log of c of t is equal to log of c of 0 plus the sum over alpha of log of 1 minus t over alpha. And then the point is that because of this correspondence, we can group the alphas together. So instead of summing over all alpha, I'm only going to sum over the real part alpha greater than 0, so only over the positive ones, positive alphas. And therefore, I have a term with a plus alpha and a term with a minus alpha. And then, therefore, if you just do kind of definition of logs, log of something plus log of something else is the log of the product of those two things. So if you multiply these together, you get log of 1 minus t squared over alpha squared. So that's how you get this equation here. So you start with the single roots by themselves, but because you have this even function symmetry, then you can group them with a square like this. And then if you want to return to the modern xi function instead of the kind of old Riemann xi function, we're going to write the letter rho instead of alpha to denote the zeros of this xi function. And then instead of this symmetry of even functions, we have xi of s is equal to xi of 1 minus s. And therefore, we have almost the same thing as above. So we get this function, but this looks a little bit different. It's a little bit more complicated. You get log of xi of s is equal to log of xi of 0 plus the sum where the imaginary part of rho is greater than 0. So remember, because it's a rotation by 90 degrees, we change the real part greater than 0 to imaginary part greater than 0. And then you get log of 1 minus s times 1 minus s over rho times 1 minus rho. And this is just if you do the partial fraction of this thing. Okay, and then the question is, does this thing converge? And it turns out it does converge. And the reason it converges is because of the Riemann von Mangoldt formula. But first, before that, I'm actually going to mention that if you just took this sum, before you group them together, this sum actually does not converge if you go in like a random order. Now, if you go in the proper order, which is summing them each 0 with its kind of 1 minus s, the kind of symmetric 0, then it actually does converge. And here's the reason. So we know from the Riemann von Mangoldt formula that n of t is asymptotically t over 2 pi times log of t over 2 pi. And therefore, if you try to invert this, so instead of asking the question of how many zeros are there below a given number, below a given t, we're going to instead ask, what is the t value of the nth zero? And if you just invert this, you get that it's approximately n over log n. I'm doing a small abuse of notation here with this tilde sign, but I think this is fine for the purpose of demonstration here, because really there should be some constant in front here, but I'm just going to ignore it because we're just trying to check if something converges or not. And therefore, you probably know from kind of elementary calculus that these two things on the left, if you take the sum from n equals 1 to infinity of 1 over n, this is equal to infinity, so it diverges. But if you take the sum from n equals 1 to infinity of 1 over n squared, this thing actually converges. And if you take the power to be any number between 1 and 0, or 1 and 2 strictly, then it still converges. So this thing, it's not that this thing barely converges, it's that this thing barely diverges. And if it's even n to the 1.0001 power, it will converge. Okay, so this sum is what would happen if you were to sum, like if all the zeros were spaced out very linearly, then you're summing this sum like over rho would be like 1 over the sum of 1 over n. But because the nth zero is approximately n over log n, and the zeros are going to bunch up a little bit as you kind of go along the line, then this actually grows a little bit faster than this, but not much. It's just a log of n over n. So I'm just saying 1 divided by where the 0 is. And since the 0 is at n log n, I'm doing 1 divided by n over log n. That becomes log n over n. And this equals infinity because this thing equals infinity. But if I were to do the squared version, then this thing now converges because the sum of, if I do 1 over this thing squared, it's log squared of n over n squared. This thing definitely converges because this is log grows slower than any power. And therefore, this thing actually converges. And the reason it converges is because, well, I guess both of these will converge. And the reason it converges is because the thing on the denominator here is a square of where the 0 is. So therefore, we just prove that if you take 1 over the 0 squared, that series will converge. And then this thing is also like 1 over rho squared. So like if you just expand this out, it becomes rho minus rho squared. So the denominator grows like rho squared. Okay, so therefore both of these things converge, but if you sum them one at a time and don't go in the right order, then they diverge. Cool. So I'm going to say recall from episode 20, by the Weierstrass and Hadamard factorization theorems, since C of S is an entire function of order 1, which we covered in episode 19, we know that it can be factored over its roots directly as this equation. And then with some more thought about finding what this A constant and B constant are, so this is just the result of using the Hadamard factorization theorem on the C function, and getting rid of this exponential term. So if you group the roots together, then you can actually eliminate this exponential term. Then Hadamard proved Riemann's C formula in 1893. So again, this was like 64 years after Riemann's paper. So this formula. Cool, so we covered a lot today, and here's going to be the summary of these 3 paragraphs. So we just went through paragraph 3, and the summary is basically that Riemann defines the Xi function, or his version of the Xi function, which is rotated by 90 degrees, which no mathematician today uses anymore. Then he writes 4 extremely profound claims with barely any justification and certainly no proof. Okay, so the first one is this Riemann von Mangoldt formula right here. He says that the number of zeros below a given height t is approximately this, or is equal to this plus some error term, and this was proved by von Mangoldt in 1905. Okay, and then next he makes this 100% hypothesis. He says one now finds indeed approximately this number of real roots within these limits, and this is currently unknown if this is true or not. Okay, and then the next line, of course, is the Riemann hypothesis, so it is very probable that all the roots are real. And once again, no one knows if this is true, and this is the $1 million question. And then here he gets the what's now known as the Hadamard product formula in its log form for the Xi function. And this was proved in 1893. So both of these results were proved decades after the original paper, and there are still 2 results here that are still unproved. So that's it for today.